Last time we grew a single decision tree. It was clever, but a little shaky. Today we fix that with a simple, powerful idea. Instead of one tree, grow a whole forest and let them vote. Here is our data again, two colors mixed together. A single tree carves a boundary like this. It works, but look how jagged it is. It bends around almost every point. And here's the problem. Change the data just a little, and the whole boundary jumps to a new shape. One tree is unstable. It swings with every wiggle in the data. So how do we make a forest of trees that are not all the same? The first trick is called bagging. Think of every row of data as a chip in a bag. To build each tree, we draw a fresh handful from the bag, but with a twist. After each draw, we drop the chip back in. So some rows get picked twice, and some are missed entirely. Each tree ends up seeing a slightly different slice of the data, about 2/3 of the rows. The second trick is even sneakier. When a tree asks a question, we do not let it look at every feature. We hide most of them and show it only a random few to choose from. Why hide them? Because if one feature is very strong, every tree would grab it first, and they would all look the same. By hiding features, quieter ones get a turn. The trees learn to disagree, and that disagreement is exactly what we want. Put those two tricks together and we can grow a whole forest. Each tree trains on its own slightly different sample, looking at its own random features, so every tree turns out a little different from the next. A forest of rough drafts, not clones. Now a new point arrives, right in the tricky middle zone. How does the forest decide? Simple. We ask every single tree, and each one casts a vote. Some trees say green, a couple say red. No single tree has to be perfect. We just count the votes. 5 trees say green, 2 say red. The majority wins. The forest predicts green. The final answer is just the most popular vote. Here is the real payoff. Each tree on its own draws a jagged, shaky boundary. Pile all of those wobbly boundaries on top of each other. Their wiggles point in different directions, so they cancel out. What is left, in the middle, is one smooth, steady boundary. The forest is far calmer than any single tree. That is how voting turns many shaky guesses into one confident answer. There is a neat bonus too. Remember, each tree missed about 1/3 of the rows during training. Those left-out rows are called out of bag. Since each tree never saw those rows, we can quietly test it on them. Gather that up across the forest, and we get a free, honest score without ever touching a separate test set. One last question. How many trees do we need? As we add more trees, the error drops and the forest gets steadier. But only up to a point. Soon the curve flattens out. After that, extra trees cost memory and time without making things much better. So we add trees until the curve goes flat, and then we stop. So a random forest is just many different trees, each trained on its own random slice, all voting together. Diverse, steady, and hard to fool. A single tree can wobble. A forest holds its ground. A forest lets its trees vote all at once, as equals. But what if the trees worked in a line instead, each one fixing the mistakes of the last? That is gradient boosting, and it is next.